this computer. Hello, good evening, good afternoon. It is Tuesday, 10th of November. It's 4 p.m. in Davis, California. Fall is here. We had the first below freezing temperature. It was minus 0.5 centigrade, but that's deep freezing Davis. This morning, today we continue our recording of lectures on modeling and simulation, realistic modeling and simulation of earthquakes, solid structures, and their interaction. Today we're going to hear Mr. Wang talk about stochastic elastic plastic wave propagation using real easy. So to introduce you all, Heshen, say hi.
Hi, good afternoon, everyone.
Hello, we have Dr. Han Yang.
Hello, everyone.
Stay a little bit longer because your picture did not show up. So say
okay.
There you go. Now you're in. Good, excellent.
Okay.
And we have Yusheng Yang, our visitor from Tongji.
Hello, guys. How are you doing?
It still didn't show up, but that's okay. Okay, I guess I don't know. Zoom is tricky. Anyway, so okay, so Heshen, maybe you can start sharing your screen. I need to allow that.
Okay.
Okay.
Okay, I will use this device.
So what Heshen is going to do, he's going to go through initial set of slides, and then he's going to actually run an example sort of live, the first few hundred steps, and then he's going to show results.
Yes. So, okay. So now you can see my screen.
Yeah, right? I see your screen. That's right.
Okay.
Make one slide per page or something like that, so we don't. Okay. Okay, so go ahead, please.
Yeah. So good afternoon, everyone. So today we're going to continue to talk about our stochastic finite element modeling. Specifically, we're going to use the example to show you how to use the real easy to do stochastic elastoplastic wave propagation. And so this is the example that we're going to present today. So we have a 3-layered nonlinear elastoplastic site. We're going to use we're going to consider in the uncertainty in this elastoplastic material, and also we want to consider in the uncertainties in the seismic motions. And we're going to input both of these uncertainties and represent them in polynomial chaos inside the real easy. So
yes.
so on the uncertain material side, we're going to use the uncertain elastoplastic material as we presented before. It's a vanishing elastic region, a nonlinear Armstrong-Frederick kinematic hardening model, and it has 2 parameters. Number 1 parameter is the uncertain parameter HA, which will control the uncertain initial stiffness, and also we have the uncertain parameter for the shear strength. So here you can see we're considering the 3 layers with different, the mean and the coefficient of variance for these different layers of the material, and then we also consider the correlation between the different layers. So we're going to discretize this soil site with 10 elements, and they model the site response using the 1D stochastic shear beam element. And as I mentioned before, so we're going to consider both of these random variables, the HA and the CR, at the marginally log-normal distributed random variables. And then we're going to assign the correlation structure to be exponential correlation with correlation length at 10 meters. And we also considering the uncertain input motions. So here we consider the uncertain bedrock motions from a single seismic scenario, which is magnitude 7 and distance 50 kilometers. And we simulated those time domain uncertain motions using the stochastic Fourier ampli spectrum and stochastic Fourier phase derivative model. You can see those papers for more information regarding the stochastic ground motion modeling. And so once you have all these input uncertainties, the first thing you need to, when you do your stochastic modeling, you need to properly characterize them using polynomial chaos. So here I'm showing you that we are checking, whether our polynomial chaos representation can capture the marginal distribution of the uncertain HA parameters of the soil as the first layer. And then you might also want to check, whether this probabilistic material response is expected. So here we are also checking the response of the first layer of the material, using the strain control. So as you can see here, we have both some uncertainties in the initial stiffness and also the uncertainties in the final
in the shear
shear
strength,
strength.
yes.
Yes, that's true. So you can check, here our mean shear strength is about 60 kilopascal, and that is what we assign, here at the initial input. And so that is the uncertain material. So then we also need to 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 input the uncertain seismic motions. So here we show you the first 200 realizations of the uncertain motions that we considered for this example, and we also check the marginal distribution of those uncertain realizations to just make sure they are can be well captured by the Gaussian distribution. And then it's very very important to make sure this simulated uncertain motions have the desirable amount of the variability that is consistent to the GMPE. And so once we have those realizations, then we can derive the statistics from those realizations, and then we can represent them with a Hermite polynomial chaos. So as you can see here, we are again checking the PC representation of the uncertain motion random process with the statistics got from the realization. This is the displacement, and this is the acceleration. So once you have all those input uncertainty well prepared, so then we can go to the simulation where we're going to import those uncertainties. So now you can see my example file, right?
Yeah.
So can I just add? So essentially, you check
Yes.
that all these representation of the material, uncertain material, is doing a good job. You develop the statistics of the uncertain motions, and now you're going to
Yes.
show us the input file that we're going to run first few hundred steps, and then
Yes,
show
that's
you
true.
pre-recorded or not recorded, but already run example that because it had a few thousand steps, and that takes 10, 15 or so
Yeah.
minutes. So please go ahead.
Yeah,
Yes.
that's true. Yeah. Yeah. So as professor said, now I'm going to run those input file that I already prepared.
So
So you
don't
just
run. Go back to file. Let's just show them how the file looks like.
okay.
I mean, just to discuss a little bit. So and we've seen this before, right? So go on top. Go on top. So
Okay.
here you define the model name, and then you have to define random variables.
Uh-huh.
And so this is for parameter HA for the initial stiffness, and then this is the second one
Yeah,
is
parameter
for
CR.
parameter CR, which is used to develop the uncertain
The
shear strength.
strength. Yes.
And so after that, you define the random variable, you define the random field, you define the Hermite polynomial chaos expansion.
Yes.
You go ahead, yes.
So you because we you want me first to start to run this file because it takes several minutes to finish. I mean,
Oh yes, yes. So run. Okay, so run it. So
or just
open.
run 100
Yes,
steps.
run it, and then we'll discuss the file. So go, yeah. But hold on, make this window bigger so we see when it starts to run. Make this window bigger so when we see, well, not okay, fine. So he's gonna run on easy minus F means input file, and then what's the name of the input file? Stochastic.
Yeah, I think stochastic
Plastic, yes. Motions or something. Or, yeah, wave propagation.
Okay, yeah.
So it's going to give you initial header, some information about the version of the program, and then it says down here that it is running and gives you some statistics, some logs of what is currently going on. So maybe go back to the input file. Let's just see. Let's just comment a little bit more the input file.
Yeah, that's true. Yeah, so yeah, as professor mentioned that, yeah, we're going to define the material parameters as the random variable, and assign this correlations through by incorporating these random variables into this random field, and then you do the same thing for the CR, and here you have to do the polynomial chaos Kahuna Loiv expansion for each of these random field parameter for HA and also for CR, and it's so it's quite important here is you specify the the correct information for the global dimension of the random field. For example, if you say here, I define the HA as the dimension 3, so it will corresponding to uncertainty KC1, KC2, and KC3. So, but now when you move to CR, so you need to specify the additional dimension information for the CR because now the CR should be KC4, KC5, and KC6. So you need to specify. If you look at here, I specify those dimension information through this text file. So you can open this text file. So basically here you are specifying the local dimension 1 of the CR will corresponding to the global dimension 4, and local dimension 3 will corresponding to the global dimension 6. Yeah, just to make sure the program know different source of the uncertainty and how they are aligned with each other. Yeah.
And,
Yes.
and if I just may say, we'll put these files. These files are going to be available online, so that anybody can get them and run them, and maybe make changes and try to run them. So Real Easy, which is also available online. Yes, go ahead.
Yeah, and here we are define and then after this material parameters we are define the motion. So we define the motion as the Gaussian random process. Here we specify both the marginal mean, marginal standard deviation, and the correlation. And also again you need to do the polynomial chaos expansion for the uncertain motions. And then the third part, which is very important, is you need to provide those triple product and the double product information. As we mentioned before, this you can for those triple product, double product, you can pre-compute it and save them to your computer and then load them while you're using while you need to use them. Yeah, and then with all those information defined, you can go ahead to define your uncertain. Basically, here we have the 3 different uncertain elastoplastic material, and you need and the main difference here is that now for the constitutive level, you also need to specify the triple product that you needed to do the constitutive Galerkin projection. And so once you have all those material defined, then you can move forward to do the define the whole model. So here we first define the nodes, and here a very important parameter that you want to specify is called number of response PC terms. So this is the main controlling parameter that will determine how many number of polynomial chaos terms, expansion terms that you will compute for your probabilistic response. So best definitely, the higher number you specify, the more accurate result you will get. But then the computational expense will also go up. Yeah. So we specify the first 200 leading terms of the polynomial chaos, and then we also go ahead to define the stochastic shear beam element. We have 3 layers and assign them with different stochastic material that we already defined before. Yes, Professor.
So go back a few lines. So when you define these to be 200, the number of polynomial chaos terms, you can do a simple sensitivity study and see which number gives you stable result. Again, this is not Monte Carlo. This is going to expand in polynomial chaos space, in probabilistic space. But it's a good idea to do a slight sensitivity study to see what works well for your problem. And then once you do that, then you can run you can run this, and you're going to get very accurate results very efficiently.
Yes. And then obviously you can also apply the damping. So now the damping actually become a stochastic Rayleigh damping. So this is the same idea. Essentially now this parameter alpha and beta will apply to the stochastic expanded mass and the stiffness matrix. And then go ahead. You need to specify the stochastic boundary condition. So now you need to add the stochastic.
The keyword, the stochastic keyword for the degrees of freedom. Yes.
Yeah, that's true. Yeah, because then it will fix all the expanded DOFs associated with this physical UY and UZ. And then you can move forward to the final analysis stage. So here we are specifying the uncertain input motions using the penalty method. Here you need to specify the penalty stiffness, which is suggested to be several orders or magnitude larger than your normal elemental stiffness. And you need to specify the random field, which is already defined as the random process of the motions. And then you need to define the solvers. And for the dynamic, you need to define the dynamic integrator and also the convergence algorithm. And eventually, yes, Professor.
So in this case, we are doing essentially explicit. We don't do implicit. We don't satisfy equilibrium. We do small enough steps, and this in probability space. So we define algorithm with no convergence check. So it's gonna just go each step, small steps. It's gonna go forward and do the analysis.
Yes, that's true. Yeah, and then eventually you need to use be careful. You need to use the stochastic transient algorithm.
Yeah.
As Professor mentioned that this is a pure explicit. Yeah. Okay, let's see. Yeah, so as you can see here, we already finished the first 100-step analysis, and you can go back, check your simulation file. So okay, so this is the generated HDF5 file that contain all the analysis result. You can open the node dataset, and then first of all, you can check the how many number of DOF of each node. As you can see here, now each node has a 600 DOF, which is the expanded stochastic P6 expanded DOFs, and all the polynomial chaos coefficient for the probabilistic accelerations are contained in this data set, and the displacement are contained in this data set. So once you have all those output result, you can post process this output result by just extract them using a simple Python script. So here I'm using this script to plot the surface response, the ground surface response, the displacement and acceleration. So this would be the displacement response at the ground surface. As you can see here, yeah, because the input motion, the mean is always very small compared to the standard deviation. So the response would be mainly controlled by the standard deviation, and you can notice here there is a tiny bit of the permanent displacement in the standard deviation. This is because of there's some plastification, and this plastification now becomes uncertain, and also you can here is the acceleration response of the ground surface, and so actually with all those polynomial chaos coefficient, you can also extract many other information like the marginal PDF and also the correlation information. Yes, Professor.
So go back to the acceleration response, the big one that you just showed. Yes. So this is really a fully probabilistic response at the surface. You can get it at any node, but we're looking now at the surface. And what this gives you is the mean, and then it gives you down the actual standard deviation. But each of these time steps, each of these points in time actually has a full PDF defined. So then you can use that to develop all sorts of statistics and gain a lot of knowledge and information about the uncertain response.
Yes, that's true.
And one thing to note more, what we're going to have soon is the sensitivity of this response to the input uncertainties of input parameters, meaning the uncertainties of the motions and the uncertainties of material. And that's going to give you actually quite rich picture of what is going on and what needs to be improved to get lower uncertainties if you want to do that. Yes, go ahead.
Yes. Yeah. So yeah, I think yeah, with that, I think we can conclude this example. Yeah.
Okay, good. So just to note, so we're going to put all these input files online so that people can try it out, and they can, and we'll, of course, if you go to our previous lectures, you can find explanations of how to do these things. So you can change your input motions, you can change your material, and so on. And I think we're going to make a simple app application that's actually going to give you choice of defining your own thickness, your own layers, and your own uncertainties, and then your own motions, and then we're going to do the pre-processing, and we're going to run it, and we'll give you something on the surface. Okay, thank you. So this concludes the lecture, right?
Yeah.
Well, thank you very much. So again, we'll be back sometime soon with some new lectures. Thanks again to all three of you. Thank you, Heshan, for presentation, and I'll stop recording and I'll pause these online with the next hour or so. Let's stop.